Alright, so in this section we're going to be talking about parent functions. We're going to learn and identify some of the common graphs that we often run into. There is going to be a quiz at the end of this week. There's your guide as to the things that are going to be on that quiz, so be on the lookout for that. We are going to be able to recognize today, though, some of those graphs simply from either the equation themselves or be able to actually produce those graphs given their equations. The first thing we need to start off with is just having the simple ability to write a linear equation given some values. For example, in this one here, we are given that f of 1 is equal to 3, and we're given that f of 4 is equal to 0. And so we have to write a linear equation. So we have to borrow a couple of things. First of all, we need to find out what the slope of our line is. Then after we know what the slope of the line is, we need to use a form of a linear equation that helps us write the equation based on slope and maybe based on one of the points. And that's this equation that we have here. But first, we got to find the slope. What numbers do I plug in for this? What's y? What's y1, y2, and so on? Well, remember that when you see f of 1 equals 3, that's really telling you that this point right here, if x is 1, the function value is 3, that means y is 3. If f of 4 is 0, that means 4 is x, 0 is y. So we're going to take this equation here to calculate our slope, and we do so by saying y2, and that's the second y value. Doesn't matter which one you decide is the second one, as long as you stay consistent. So the slope of this line going through those 2 points is 0 minus 3 over, so y2 minus y1, x2 minus x1, which is what? So our slope here is equal to negative 3 over 3, which is equal to negative 1. So our slope is negative 1. Then, knowing that I have a slope and knowing that I have at least one point, I can plug into this equation. So you might want to ask yourself which equation, which point and which other value am I going to use? Well, remember that this is the point slope form of an equation. That means you need one point, you need the slope. So I need m, which I just calculated, and I need any of those 2 points that I started off with. You can use literally either one of them, but there's one that's easier. And it's the one that has a 0, because it's a little bit less to do. So I'm going to go over here and say y minus, and now the y value of that point. Now if you're thinking, oh, well, y1 was over here, that's fine, you can stay with that one. But I'm going to borrow this guy instead, just because of the 0. It makes my life a little easier. I'm too lazy to do math the long way, so there's a shortcut. Here we go. And then my slope is negative 1. Do not substitute for x, but x1 from the same point is 4. Y minus 0, negative 1 times x, negative 1 times negative 4. And there is my equation of a line that goes to the points 1, 3, and 4, 0. And you can plug in those x and y values and see if those give you true statements, and in fact they will. So now let's take a look at 2 of our basic types of functions. First of all, the one that is called the constant function simply says f of x is equal to c, a constant value. An example would be something like, well, f of x is equal to 3. Well, what does that look like? I go to where my function value is equal to 3, and if you look, that tick mark runs left and right. So it's just a value of 3. In this case, it's 3 because that's the one I picked. And that line stays at the same constant value the whole time. It's a horizontal line. You can also call that y equals 3 if you would like. Same thing. Never changes. It stays constant. We talked about intervals of increasing and decreasing last time, and also constant. And I mentioned to you guys that doesn't happen very often. And here's one situation where it does. It stays at the same exact value. So we're looking at this one and we're asking ourselves, hey, what's the domain of this? What x values can I use for this? And I can use all reals. What's the range? What's the y values? What are the function values that I see? Well, in this case, the range is just whatever the constant value is. The range is just whatever value of c is equal to. In this case, we chose 3, so the range would be 3. Is it odd or is it even? Well, remember, the test for odd and even is to use, and we can start off with something like f of x, and seeing if f of x is equal to f of negative x. Also, you can look and see, is this symmetric about the y-axis, or is this symmetric about the origin? In this case, because if I plug in a negative in for x, here there's no substitution placement for x, so it's going to stay the same. F of x is in fact equal to f of negative x. It makes this function here even. What is the relative max or min? Well, I mean, you can call it either 1 if you would like, but because it stays constant, it really doesn't have a max or a min. If you want to call it anything, you can argue for c as both the max and the min. But I mean, because it never leaves that value, we almost don't even mention that. Is it increasing or decreasing? And we just answer that question. It's constant. It's not increasing, decreasing. It has no max, has no min. It just stays at the same value. So in this case, it's not doing either one. All right, for the next one, we are looking at what we call the identity function. That is where f of x is equal to x. That is y equals x. Whatever x is equal to, so is y. So that means if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. And this equation here goes right through the origin, right down the middle of the graph, splits the graph perfectly, and is always increasing from left to right. The domain is the input values I can have, and the domain for this is all real numbers. You're not going to be asked to say all of these things every time, but these are things we should understand from the basic function, and so then we later can move these things around, make some changes to it. The range, because it goes off the graph, off the chart on the left side, off the chart on the right side, and the range covers all reals as well. Is it odd or even? Well, if we try f of x and compare that to f of negative x, not going to work. Also, keep a couple of things in mind. Can't be even because, well, has an x, that's an odd power. So it doesn't even have a chance to be an even function. So I can eliminate that. Now the other option was, if I take, to find out if it's odd, I look at f of negative x. If I plug in a negative for the x, I end up with the same as if I make the whole thing negative. And when I plug in a negative here, it actually in fact makes it negative f of x. The other thing we do to check if something is an odd function, remember, it's the one where you can just look at this graph upside down. If I look at this upside down and it looks exactly the same, it is in fact an odd function. So I simply just rotate it at the origin. The thing is upside down right now, but it looks like the same graph. Let me see if I can get the graph and the line I drew. Let's try that. That's going to take the words too. Is that going to work? No. I was hoping to be able to rotate the line itself. But if I do that, it's going to take, yeah, it's taking the words too. But look, even if I do that, it looks exactly the same, words or not. Take a look, same exact graph. And all I'm doing is flipping it upside down. All right? Now, so it is in fact an odd function. And we can prove it algebraically by the substitution of negative x and comparing that to the whole thing being negative. That is, if I plug in a negative for x, f of negative x is equal to negative x. And if I make the whole thing negative, it's equal to negative x as well. So those two match, it makes it an odd function. What's the relative max and min? It doesn't have one. Because this thing is always increasing. It is increasing in the interval between negative infinity, runs off the chart to the left, runs off the chart to the right, positive infinity. Now remember, increasing, decreasing, we never include it, no matter what. But then on top of that, it's infinity. So because it's infinity, well, I don't know where that is, so that's always going to be parentheses for those. And like we said, for this one, it is increasing. So the red graph is increasing. For the blue graph, we didn't mention that. We mentioned it but didn't write it. It's neither. All right. The next one is a very familiar graph to us. It is the quadratic function. It is f of x equals x squared at its most basic equation. It's just x squared, nothing's been done to it. Let's take a look. If we needed to graph this, sometimes the best way to do it is to make a table of values where we have x and we have f of x. And in that table of values, good general rule of thumb is if you're going to plot, make sure you have enough points on there, and I want to use from -2 out to +2. So I have -2, plug it in, it's 4. -1, plug it in, it's 1. 0 squared, 1 squared, 2 squared. And we plot those. Let's take a look. We go -2, 4, 1, 1, 0, 0, -1, 1, 0, 0, 1, 1, 2, 4. And then we connect those, and because it is slightly changing, if we remember from quadratic functions, it's kind of like a U shape. It is not straight lines. It does kind of round out towards the middle. It is what we often call a parabola. And this is what we end up with. The domain, asking for the x values, what is this domain of this graph? It is all real numbers. There's no limit. There's no restrictions that I need to consider. Now, for a basic quadratic function, the range is restricted. Again, when I square a number, I basically get rid of negative values. So the range is from 0 to infinity. And because I can square 0, it is included. And infinity, I don't mention that as being included anyway. So remember, brackets means it's included, so the range goes from 0 to infinity if we're using interval notation. You can also say y is greater than or equal to 0, but we rather use the interval notation instead. Is this odd or even? Well, we can look and see, is this symmetric about the y-axis? Or is it, if I turn upside down, am I looking at the same thing? This one looks like a mirror image on both sides. This is an even function. But now, if we want to try that algebraically, the test for even is f of -x has to be equal to f of x. So if I use a negative in this equation, f of -x, that means I have parentheses -x and then square it in place of just the regular x squared. I substitute a -x. When I square a negative, what happens? It goes away. So negative times a negative is in fact x squared. And if you notice, if I put in a negative in for the x, I end up with the same exact equation I started off with. That in fact makes this function even. Also, as we said, if you can fold it over the y-axis, it match. If if it's a mirror image on both sides, then it makes it an even function. Does it have a relative max or min? In this case, for standard quadratic functions, it has a min, and the min happens at the lowest point that you see, at that turning point of our quadratic function. In this case, it just happens to be the lowest value of my range because it runs to infinity without bound, runs to positive infinity. So in this case, the relative minimum value is 0. Is this increasing or decreasing? And the answer to that is both. It is increasing from 0 to positive infinity. It is decreasing from negative infinity out to 0. Now be mindful of this. Infinity I'm never going to include anyway. But remember, in points of intervals of increasing and decreasing, when we get to the 0, is it going up? Is it going down? Is it increasing, decreasing? What's happening there? Because that is a point where change happens. We cannot say one way or another. We never include 0 in intervals of increasing or decreasing, which is different than the range. In the range, if it's part of the graph, we include it. But in increasing, decreasing, I cannot tell you if it's going up or down at 0 because it's not really doing anything. It's not doing either one. It's also not staying constant because it's just one value. But if I step forward from 0, I know it's going to start going up. If I step backwards, I know it's where it was coming down. So I can't include 0. This just shows that 0 is where that change happens. Then we have the cubic function. The cubic function, I like to call this one the S curve. For this one, again, same thing. I want to make a table of values because might not really know what this one looks like. So I'm going to pick some values for x. My input values are going to be -2, -1, 0, 1, 2. Then I'm going to find out what happens when I plug those in. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Well, some of these numbers are looking familiar and repeating, but at the same time, we got a difference in signs. So let's see what happens when I plot these. -2, 8, -8. -1, -1. 0, 0. 1, 1, and then 2, +8. So this one starts off here. When it gets to the middle here, it kind of flattens out a little bit, and then it goes right back up rapidly, because now we're taking every number and cubing. For that matter, if I get to 3, and I didn't choose that, but 3 cubed is 27. That's way off the chart. So it gets, up pretty fast. The domain, there's no restrictions. It is all real numbers. The range, look at the lowest y value, look at the highest y value. Well, it's all of them. Is this odd or even? If I fold it over the y-axis, not going to match. So the other option I have is, well, let's turn ourselves upside down. Let's not move the graph. Let's try to turn upside down, see what happens. Move this rotating point here. If I turn this graph upside down, does that look the same as it did before? It looks exactly the same. Doesn't matter how my graph is oriented. Looks pretty similar. I'm trying to get the... There we go. That's what I wanted to do. So now what I've done is I simply just flipped my graph upside down. Check it out when I undo and redo that. The graph minus, my bad drawing, looks exactly the same if I just flip it upside down. That's one way to check if it's odd, if it's symmetric about the origin. That means that when you have x at 2, 8, or x at 2 and y at 8, you also have -2, -8. There's a mirror image on the opposite side of the origin. Now, algebraically, we can prove that by saying f of -x is equal to -f of x. Let's take a look. F of -x would be -x and then cubed. So f of -x is equal to, when I take a negative to the third power, it stays negative. I get this equation. Now look what happens when I go and try to do -f of x. That is telling me to take the whole function, which is x cubed, and make it negative. So -f of x is equal to -x cubed. Notice right here, f of -x and -f of x match. They're exactly the same. That tells me that this is an odd function. Relative max or min, neither one. It is always changing, and for that matter, that change is always increasing, and it is increasing from the interval of -infinity to +infinity. All right? The square root function. This one, a little bit of care. You got to be careful with some of the numbers. For this one, if I made a table of values to try to graph this guy, I might say x and I might say f of x. And then I say -2, -1, 0, 1, and so on. And so, okay, I go -2, take the square root of that, and you're like, oh, wait a minute. Nope. So our standard points for just finding out what's what our table is going to look like, or our value, our graph is going to look like, is just not going to work. Also, if I know I'm dealing with a square root, I know I need to have those numbers be positive, so I can start at 0, 1, 2, and so on. And so you're like, okay, square root of 0 is 0. Hey, that's a good number. Square root of 1 is 1. Hey, that's a good number. Square root of 2 is not a good number. Instead, I might not want to graph the square root of 2. Instead, I want to know what's the next number that I can take the square root of. And so I can take the square root of 0, I can take the square root of 1, I can take the square root of 4. Square root of 4 is 2. And you kind of start seeing a pattern here. So maybe I want 3 next. So what number gives me 3 as the result of the square root? Square root of 9 is 3. So it's kind of unconventional. This time I needed to pick values that I could get answers for, but I ended up picking the y values more so, because I was thinking ahead to numbers I can take the square root of. So I start off at 0, 0, then 1, 1, and then 4, 2, and then 9, 3. I call this one the rocket, because it looks like it's just a rocket just taking off from the ground, and it's going to go horizontally a lot faster than it's going to go vertically. The domain of this guy, the x values are limited to only positive values because it's a square root, and I have to keep the number inside the square root positive. So I start off at my break of positives and negatives, which is 0, and then the domain runs to infinity. Infinity is never included. 0 can be. I can take the square root of 0. 0 is part of the graph. The range is the same thing. The lowest value this ends up having is 0. The highest value this ends up having is very slowly, but it does go to infinity. Is this odd or even? Well, doesn't match over the y-axis. If I turn it upside down, it looks different. There's not a copy on the other side of the origin. Algebraically, f of x would be equal to f of negative x if it was even. That is, well, that looks different. Square root of negative x is not the same as square root of x. Also, in order for it to be odd, f of negative x would have to equal to negative f of x. So f of negative x, we just calculated that, is the square root of negative x. And then negative f of x is negative square root of x. These two things are not the same. So it's not odd either. In that case, it's exactly that, neither. Does it have a relative max or min? It does. It has a lowest value of 0. Is it increasing? Is it decreasing? It is always increasing, but it's only increasing through its domain, which is from 0, oh, made a mistake, from 0 to positive infinity. But remember, at 0, I don't know what's going on, it just started. You never include those anyway. So it is increasing from 0 to infinity. Neither one of those are included. I was looking at the domain and I thought, oh, I'll just copy that, right? Well, no, don't just copy that. So 0 is not included, neither is infinity, because we're talking about intervals of increase and decreasing. You don't know if you're going to go up or down when you're just starting until you take that first step. The next one we have is the reciprocal function. What the reciprocal function is 1 over x. Instead of x, it's the fraction upside down. Instead of x over 1, it's 1 over x. We make a table of values for this one. We have x, we have f of x, and if I make my standard table of values, I have -2, -1, 0, 1, and 2. Now something happens with this one here at 0. -2 becomes 1 over -2, or -1/2. -1 becomes 1 over -1, or -1. At 0, it becomes 1 over 0, which is undefined. At 1, it's 1 over 1. At 2, it's 1 over 2. So let's just take a quick look. First of all, at 0 is undefined. So in this one, I can, by knowing what this guy here does, at 0, that value has to be taken out of the entire graph. I cannot use 0 at all. It is undefined at 0. It becomes what we call an asymptote. At -2, I'm at -1/2. And then at -1, I'm at 1. But then what happens as I get closer to 0? Well, if I use 1/2 and then flip that upside down, it becomes -2. And if I use 4, it becomes 1/4. If I use 10, it becomes 1/10. It turns out that this guy has a second asymptote. And I'll just draw a dotted line. A second line it approaches. It gets really close to the x-axis but never touches. Really close to the y-axis and never touches. Alright, so let's make the asymptote for this one also red instead of the one I drew. Likewise, on the other side, I go to 1, 1. I go to 2, 1/2. And if I go to 1/2 and flip, that's 2, and so on. If I go to 1 over 4, it's doing the same thing it did on the other side, except that the numbers are positive. So it's going to get really close to, and that was a little shaky there, but you get the idea. Really close to the x-axis on the positive side of things. What's the domain? Well, the domain is every number except for 0. So you can say x not equal to 0. If you want to use interval notation, you would say from negative infinity to 0, then again pick up at 0 to positive infinity, and you use parentheses around the x. It would look like this. Negative infinity to 0, not included. And then 0 to positive infinity, not included. That would be the domain. That's how we show every number except for 0. Just use the parentheses. The range, likewise, this time y cannot equal to 0. The only way to find out if y can equal to 0 is you set the top equal to 0, and because the top is always 1, it's not going to be. So same thing, from negative infinity to 0, then from 0 to positive infinity. Odd or even does not match over the y-axis, but it looks like it matches across the origin. If I was to rotate this upside down, or turn myself upside down, which is more of a challenge. If I was to rotate this, oh, look at that. That one took the graph with it. I'm glad it did that. So let's rotate this. Let's undo and redo that. Does that graph look the same when I just flip it upside down? Notice the numbers are going upside down. The graph looks exactly the same. That's a quick check for, and I'm going to leave it upside down just for fun. It's a quick check to see if it's an odd function. Turn yourself upside down. But if you want to do this algebraically, remember for odd, the test is negative f of negative x has to equal to negative f of x. So if I plug in a negative in for x, I get 1 over negative x, which is equal to negative 1 over x. For negative f of x means I make the whole thing negative. And you're already seeing it. Negative 1 over x. Those two things are equal. That makes this odd. Does it have a relative max or min? And the answer to that is no. It runs to infinity on both sides of this graph, both the top and bottom, without bound. Is it increasing or decreasing? This is tricky. We look at this graph, and from this side here, down here, it looks like it's decreasing. We look at this graph, we pick up again on the other side of 0, on the right side of 0, and this graph looks like it's decreasing. So this is always decreasing, and it does so through the entire interval. But keep in mind, we can't use 0, so it is decreasing from negative infinity. And you almost want to say to positive infinity, that's true. But because we don't have 0 in the equation, we have to just skip that step. Or skip the 0. Pick up again, it's decreasing from 0 to positive infinity. And 0 is not even defined in this function. So it's even better to know that I'm not going to use it. So, but either way, even if it was defined, you still cannot include 0 in an interval of increasing, decreasing. All right? Almost done. The other one that is kind of tricky is the step function. But to us, it's known as the greatest integer. That is, f of x is equal to, looks like a double bar absolute value. This means the greatest integer of x. That is the greatest number, a whole number that you've gotten to when you're maybe at a decimal, and so on. A couple of examples I have for you. I love, playing games. So, and one of my favorite things to do when I'm playing video games is to level up. I like working towards the next level. I want to level up, bring my game to the next level. But this is what happens. You start off at experience level 1. And as you're progressing through experience level 1, halfway through it, you're at level 1.5. But ask yourself, what level are you when you're at level 1.5? You're still level 1. Then when you get all the way to level 1.99999 or almost to level 2, as soon as you have enough experience to end level 1, you instantly jump up to level 2. Same thing with level 3 and so on. You always jump up to the next level. It's not a gradual increase. You're staying at level 1, level 2, level 3 until you get enough to jump up to the next level. Same thing with the other example I have is when we're talking about, your high school grade. You start high school, you're in the 9th grade. And, November and December and then January, February, March, April, all those months roll around, you're still in the 9th grade. Even though some time has gone by, you don't say, I'm a freshman and a half. Unless you're just really tall. But as you're working through your 9th grade, 10th grade year, you're going to be in that same grade level until you complete the grade. So what does that look like? Well, level 0. Stay at level 0 until you get to the end of level 1, or level 0 where you jump up to level 1. Same thing, stay at level 1 until you finish level 1, then you jump up to 2, and then you jump up to 3, then you jump up to 4, and so on. And you keep doing that because you stay at the same integer level until you complete that level. And you're going to keep doing that, and it's starting to get annoying. But at the same time, you can take a close look at what does this look like when we are done plotting all these levels. Looks like steps. Likewise, if you're underground, you're still at one level below the ground until you get to the end of that. When you get close to 0, then you can jump up. It's just a little bit backwards when it comes to integers. And we're dealing with negative values, negative integers for that matter. It's a little bit backwards. And I'll go ahead and graph all of these just because it would make my graph feel incomplete if I didn't. But same thing, the only difference is that you're running backwards on the negatives. So the question I might want to ask you here, I don't need to make a table of values, but let's say if I ask you what is the greatest integer that I've gotten to, what level am I at 3.2? The greatest integer or the greatest level I've achieved at 3.2 is 3. However, when it comes to negative 3.2, let's say we're underground. What is the greatest integer you've gotten to at negative 3.2? Well, you almost want to say negative 3, right? But this is not absolute value. If I'm at negative 3.2, that means that I'm right in here between 4 and negative 4 and negative 3. What level am I at? The last level I've passed was negative 4. I haven't quite gotten to negative 3. So for this one, this is equal to negative 4. It's like I said, it's different and backwards when it comes to the negatives for this. Let me try to move this up because now I'm running into my other stuff. There we go. All right, so what is the domain of this? All right, domain of this is all reals? Yes, it is. I can use any x value I want. What about the range? Can I use all reals? The range, because again, I stay at one level and then I instantly jump up to the next level. It's not all reals, but it's all integers. That means only whole numbers, positive or negative. Is this odd or even? It's not even. And we're almost tempted to say odd, but look at the slight difference here. And this might not work. Did not mean to write. This might not work, but we're going to try it anyway. Hopefully it does. Let's try to rotate this thing. Nope, didn't take the steps. Oh, come on, stop moving the graph. There we go. I think that might have grabbed the, there we go. It left one step behind. Always one step behind. So just ignore that for a second. Because I do want to show you what happens when I flip this upside down. Notice how it is now. Look at my points now. They're reversed. When I flip this, oh look, that is not the same. This thing is moving. So yeah, it's reversed. It's close. And yeah, my numbers went with it. It's all sorts of goofy, but that's fine. The idea is for us to be able to look at this upside down, and we notice it's slightly off. This is neither. Algebraically, it's a little harder to prove. But again, you would plug in a negative for x and negative on the outside. It's close again, but it's not going to match. Does it have a relative max or min? Not really. Because it's basically stair steps and it keeps changing, but it's always at an integer level. Is it increasing or decreasing? That's interesting. Increasing or decreasing? What do you think? As x progresses, is that increasing? Then it jumps. Is it increasing? Then it jumps. Is it increasing? No. This is constant through every integer level. It is not increasing. It is not decreasing. It stays constant between every value from -4 to -3. It stays constant. Then it jumps up and it stays constant again. But through each interval of x, each section between even like 5 and 6, it stays at the same constant level. Then it jumps up and it stays constant again. So the graph stays constant at several steps throughout the equation. We mentioned this one, the piecewise function has to be done, as it says, in pieces. A piecewise function has to be graphed based on restricted domains. So we have two portions of the graph. Let's make this the first one, where we're going to say x, and we're going to say 2x plus 3. And it says that my values for x are less than or equal to 1. So it's exactly what you need to do. Pick values that are less than or equal to 1. So 1, 0, and we'll say -1. And we plug those in. 2 times -1, -2 plus 3 is 1. 2 times 0, 0 plus 3 is 3. 2 times 1, 2 plus 3 is 5. So for the top equation, I get these points. -1, 1, 0, 3, and 1, 5. But you got to be careful. Can I use 1, 5? Because it says less than or equal to, yes I can. Then I also know that my values for x are less than or equal to 1, so my graph is going to run off this way. Does not continue that way because I have to stop at 1. Then I will go ahead and graph the second portion of this, which is x and then -x plus 4. This time the values are greater than 1. So 1, 2, 3. Even though it says greater than 1, you should still see what's going on right at 1. Negative of 1 plus 4, so that's -1 plus 4, or 4 minus 1. Negative of 2 plus 4, 4 minus 2, 4 minus 3. So we go to 1, 3. 1, 3. The difference is, this time it cannot be equal to. So I'll put an open circle to show that. Get as close to the 1 as I can, just can't use it. So next is 2, 2, and 3, 1. And this does not continue below 1, so it's going to continue greater than 1. So I get two graphs that are pieced together to generate the entire picture. All right? It's called piecewise because you have to graph it in pieces based on restricted domains. All right, so let's see if you know what these guys are. At this time, if you would like to pause and try to name them all, this would be a perfect opportunity to do that. See if you remember the names just based on what the equations look like. There is one we did not really mention, but I think you're going to recognize it because I talked about it when describing a different one. Pause now, or forever hold your pieces of paper. Here we go. X cubed. What is x cubed? What is that called? That is the cubic function. What is f of x equals 1 over x? That is the reciprocal. What is this one with the double bars and so on? This is called the greatest integer, or the step. This one with a single bar is the one that I referred to when I said, hey, that one with a double absolute value. No, there's no such thing. That is the greatest integer. This is, in fact, with a single bars, the absolute value function. We didn't graph this one today, but it is one that we often see. X squared, it is the quadratic, sometimes called the squaring function, because that's literally what you do. You're squaring it. F of x equals x, that is the identity. F of x equals c, same value the whole time, a constant value. Now c is often going to be replaced by a number, whatever that is. And this one is the rocket, the square root. Starts from 0 and just takes off. All right. So hopefully you were able to name all of those just based on what the equations look like. The other important thing that we want to make sure we can do is graph the general equation, because at some point we're going to learn how to make those equations move. We're going to transform them. We're going to make them go up, down, left, right, stretch, shrink, all that stuff. But we have to first know what the original is supposed to look like so we can make changes to them later. So there's a homework assignment. It is on page 65. These are the odd problems. They are to be done on WebAssign. They have been listed for you guys, so please check out the homework on WebAssign. But if for any reason you want to see what they look like on the textbook, they're the same problems. I always give you the odds so you can check the back of the book for answers. And just have questions ready next time.